Welcome to the introductory session to interpreting the ECG. By the end of this session, you should be able to identify the components of a 12-lead ECG and begin to consider Einthoven's triangle. The first thing we need to consider is the direction of electrical flow. There is a simple rule we need to learn now to understand ECG patterns. When an electrical impulse travels towards an electrode, then it is a positive or upward deflection. When an electrical impulse travels away from the electrode, then it has a negative or downwards deflection. If the electrical current travels past the electrode, the deflection will be biphasic. If the deflection is equally up and down, or equally positive and negative, then we call it equiphasic. At this point, let's begin with the very first ECG, and the inventor of this technique, William Einthoven. He was a Dutchman who won the Nobel Prize in Physiology and Medicine in 1924 for his discovery of the mechanism of the electrocardiogram. Although later technological advances brought about better and more portable ECG devices, much of the terminology used in describing an ECG originated with Einthoven. His assignment of the letters P, Q, R, S and T to the various deflections are still used today, and the term Einthoven's triangle is named from him. Einthoven's triangle is made from the three limb leads, the two arm leads and the left leg lead. The right leg lead is a neutral lead and is not used for ECG analysis. Leads 1, 2 and 3 are called the limb leads. The electrodes that form these signals are located on the limbs. The limb leads form the point of what is known as Einthoven's triangle. From these three limb leads we get 6 different viewpoints. Lead 1 is the voltage between the positive left arm electrode and right arm electrode. Lead 2 is the voltage between the positive left leg electrode and the right arm electrode. Lead 3 is the voltage between the positive left leg electrode and the left arm electrode. Leads AVF, AVL and AVR are the augmented leads. AV stands for augmented vector and F, L and R for foot, left and right. They are derived from the same 3 electrodes as leads 1, 2 and 3, but they use Goldberg's central terminal as their negative pole, which is a combination of outputs from the other 2 limb electrodes. Lead augmented vector foot, or AVF, has the positive electrode on the left leg. The negative pole is a combination of the right arm electrode and the left arm electrode. Lead augmented vector left, or AVL, has the positive electrode on the left arm. The negative pole is a combination of the right arm electrode and the left leg electrode. Lead augmented vector right, or AVR, has the positive electrode on the right arm. The negative pole is a combination of the left arm electrode and the left leg electrode. Together with leads 1, 2 and 3, augmented vector leads AVR, AVL and AVF form the basis of the hexaxial reference system, which is used to calculate the heart's electrical axis in the frontal plane. This is how the standard 12-lead ECG will look. Take your time to orientate yourself to this. When you're analysing an ECG, you should be commenting on all the components. Somewhere on the ECG will be the setup information. On this ECG we can see the setup information of 25 mm a second and 10 mm a millivolt. The bandwidth for this ECG is 0.05 Hz to 100 Hz. Somewhere on the ECG are calibration markers, which will be looked at in a moment. The limb leads, as we have just discussed, are on the left-hand side of the ECG. The chest leads or the precordial leads, are on the right-hand side of the ECG. Along the bottom of a 12-lead ECG is a rhythm strip. This is a 10-second continuous reading that is used for rate and rhythm analysis. It will be labelled which lead it is, and in most cases is an extension of lead 2. Finally, to aid our interpretation, in between each lead is a dividing marker, indicating where one lead finishes and the next lead starts. Be careful analysing complexes at these intersections, as they often look bizarre. This should be revision from your reading of the SCST guidelines. You should be familiar now with where limb leads are placed. Again, this should be revision from the SCST guidelines. Make sure that your technique begins with the correct identification of the angle of Louis. From here, you can identify the fourth right intercostal space for V1 and the fourth left intercostal space for V2. Next, place V4 in the midclavicular line at the fifth intercostal space. V3 can then be placed between V2 and V4. Using the horizontal line of V4, place V5 in the anterior axillary line. And finally, V6 in the mid-axillary line. At this point, I want to introduce the concept of calculating the cardiac axis. We have already said that in the normal heart, the direction of impulse is generally in this direction. The normal cardiac axis is somewhere between minus 30 degrees and plus 90 degrees. In later sessions, we'll be looking at calculating the electrical axis. You'll be learning the diagram shown here off by heart. We call this the hexaxial reference system. I would like you now to have a go at drawing a 12-lead ECG. From memory, on a blank piece of paper, try to remember where the leads are normally displayed on the ECG. What additional information is added to the ECG printout? I would suggest that you pause the presentation now and continue the presentation once you have drawn your ECG. Here is the standard ECG. How did you get on? Did you remember the setup information down at the bottom here? Did you also remember the calibration markers? Let's have a look at the ECG paper. ECG paper is standardized. It is generally drawn with pink lines. When we look at the setup information on the 12-lead ECG, we said that 25 mm a second is normal. This means that 25 mm of paper equals 1 second in time. The ECG paper is made up of many squares. The large squares are 5 by 5 mm and equal to 0.2 seconds. The small squares are 1 by 1 mm and equal to 0.04 seconds. You need to know these timings and measurements as they're fundamental to your ECG analysis, so make sure that these are committed to your memory. On an ECG recording, the machine will add calibration markers. These are not physiological events, but machine-added information. The calibration marker will give us information about the speed of the ECG and the voltage. Standard ECG setting is 25 mm a second and 10 mm a millivolt. In this setting, you'll have a calibration marker that is 10 mm or 10 small squares high and 5 mm or 5 small squares wide. In almost all ECGs, this is what you will see. There are two situations you may encounter where a different marker is given. The half standard marker is a stepped marker, and this means the machine or the operator has changed the voltage setting. This may happen automatically in an ECG with very tall or very deep complexes, where without adjustment the complexes would clash with the lead above or the lead below. If the ECG speed has changed from 25 millimeters a second to 50 millimeters a second, then you'll have a calibration marker that is 10 millimeters wide. Finally, in this session, let's have a brief look at the ECG complex. This is the standard ECG complex. We have a P wave, a QRS complex, and a T wave. We also have a PR interval and a QT interval. Finally, you'll see a PR segment and an ST segment. We will be looking at the electrical activity closely next week. For now, we will say that depolarization is the point in the electrical cardiac cycle the electrical impulse is released, and repolarization is the point where the cells recharge for the next impulse. The sequence of events should be familiar to you from the physiology session earlier. We know that in sinus rhythm the SA node fires first and depolarizes across the atrium, the right atrium, and through Bachmann's bundle to the left atrium. The AV node slows the signal down and is the gatekeeper and hopefully the only communication channel between the atria and the ventricle. The wave of depolarization then spreads through the bundle of His and down into the bundle branches, through the right bundle branch and the left bundle branch, which divides into the anterior and posterior fascicles. Depolarization will then spread through the myocardium to the terminal Purkinje fibers, and finally repolarization will then occur of the ventricles. We can now put our knowledge of the conduction system together with the ECG complex. The P wave is atrial depolarization, with depolarization across the right atrium and the left atrium. The PR interval is the pause period where electrical activity is conducted through the AV node. The QRS complex is ventricular depolarization, beginning with the initial septal depolarization in the Q wave and through the right bundle branch and the left anterior and posterior fascicles to the Purkinje fibers. The T wave is repolarization of the ventricles. Atrial repolarization is not normally seen as it coincides with the QRS complex and therefore is lost to sight. This is the end of this session. In the next session, we'll take a deeper look at the ECG complex.